What makes Proxima B interesting is that it's an Earth-like planet orbiting the nearest star to the Sun. This planet is definitely the closest planet to the Sun that's not orbiting the Sun. This one, though, is different. It's special because it's really our neighbor, a fascinating planet similar to ours, located in the great expanse of space just over 4 light-years distant. Like our own planet, this distant relative of Earth is capable of supporting life. This is Proxima B, an Earth-like world that has long been a source of fascination, orbiting Proxima Centauri, the star nearest to our Sun. We found it via mathematical models rather than by first-hand observation. Recent discoveries from the James Webb Telescope, however, have clarified some remarkable features and added to the enigma. Is there life on this far-off planet? What would such life forms look like if they existed? Now that the James Webb Telescope has published a true image of Proxima B, we can see it much more clearly, and it's not at all what we imagined. What do we currently know then? Let's begin the amazing exploration of today's Earth's second planet, Proxima B, the nearest known star to our solar system. Proxima Centauri is only 4.24 light-years away. It is a faint red dwarf star that is significantly smaller and colder than our Sun, and it is a member of the Alpha Centauri system, a triple star system that also includes Alpha Centauri A and Alpha Centauri B. Because of this, it is difficult to see with the unaided eye. However, Proxima Centauri is now the subject of considerable research due to technological developments in modern astronomy, with telescopes that are sensitive to red and infrared wavelengths providing a closer look. Although the star has been known to us for more than a century, it was first discovered in 1915 by Scottish astronomer Robert Innes. We have only recently started to fully comprehend its potential, especially with regard to its planetary system. How did we end up where we are now, then? Let's get started. Astronomers started paying more attention to Proxima Centauri's minute movements in the early 2000s, especially the star's positional wobbles. This might not have seemed like much to the ordinary eye, but the specialists seeing across the galaxy knew exactly what it was. They implied that the star was surrounded by invisible worlds. The motion of the star was being affected by the gravitational pull of circling bodies. As the intensity of these observations increased, it became evident that Proxima B, the planet of Proxima Centauri, may be among the most promising exoplanets in the hunt for extrasolar life. In 2016, astronomers at the European Southern Observatory made the discovery of Proxima B. It's interesting to note that they didn't actually see the planet. Instead, they measured the tiny changes in the star's light spectrum as it moves slightly in response to the gravitational pull of an orbiting planet. Using the radial velocity approach, the data came from sensitive spectrometers on ground-based telescopes, such as the La Silla telescope in Chile. Although the faintness of Proxima Centauri itself and atmospheric distortions made it challenging, despite the amazing discovery of Proxima B, we still didn't fully grasp the planet. Only indirect measurements such as the mass, orbital period, and distance from the star Proxima B could be obtained by Earth-based telescopes. However, these observations were unable to provide comprehensive information about the planet's atmosphere, surface characteristics, or potential for life. Space-based telescopes, the next frontier of exploration, would be useful in this situation. Astronomers had long hoped that new technology would overcome the limitations of ground-based observations. Here comes the James Webb Space Telescope. By avoiding the interference of Earth's atmosphere, James Webb provides a clear, more detailed view of the exoplanet, enabling astronomers to probe its atmosphere, study its chemical composition, and investigate whether Proxima B might possess the conditions necessary to support life. James Webb's advanced infrared astronomy capabilities have already started to reveal new and startling details about distant exoplanets, including Proxima B. Are we alone, then, or is there another individual out there? Let's take our time answering this question. In order to validate or disprove our assumptions, we must first determine what enabled us to gather the evidence, and why we should have faith in it. The history of the James Webb Telescope, the spirit of exploration that characterized the 20th century space race, is being carried on by the James Webb Space Telescope. Ironically, the excitement around space travel has long since faded, so much so that by the start of the 21st century mankind would have inhabited the moon and even other planets, according to Stanley Kubrick's 1968 film 2001, A Space Odyssey. Naturally, space fever subsided long before such a project could be completed. However, visionaries persisted. The brightest minds on the planet are working tirelessly to explore every inch of space, which is the last frontier. We got our first space telescope as a result, the Hubble Space Telescope, which was launched on April 24, 1990. It transformed our understanding of the cosmos by enabling us to study far-off galaxies, stars, and other celestial bodies with unparalleled clarity. At roughly 547 kilometers from Earth, Hubble's position outside of Earth's atmosphere offered a distinct edge over ground-based telescopes, enabling high-resolution photographs that showed the universe in all its splendor. It has, of course, produced some of the most important discoveries in contemporary astronomy. Its discovery that the universe is expanding and expanding faster was one of its most famous contributions. Our knowledge of the universe was drastically changed by this finding, which was made in the late 1990s. It also helped identify dark energy, the enigmatic component responsible for this fast expansion. In 1995, Hubble also produced the breathtaking Hubble Deep Field Photograph, which revealed the grandeur and complexity of the cosmos by capturing hundreds of galaxies in a small area of the sky. In addition to these groundbreaking discoveries, Hubble has played a significant role in establishing the universe's age, offering vital information that points to a universe that is roughly 13.8 billion years old. It has clarified the processes involved in star formation, studied the movements of galaxies, and advanced our knowledge of exoplanet atmospheres. Hubble's observations have improved our understanding of supernovae, black holes, and the complex mechanisms underlying the universe. Hubble, however, has built-in drawbacks. Although it transformed our knowledge of the cosmos, its outdated technology made the construction of a new, more sophisticated observatory necessary. Despite being revolutionary, Hubble's primary observation wavelengths are the ultraviolet, visible, and a tiny fraction of the near-infrared. This makes it difficult for it to see through the dense clouds of dust that frequently block off star-forming regions, far-off galaxies, and the centers of active galactic nuclei. Furthermore, even with sporadic upgrades, parts of Hubble's gear and equipment were outdated, having been built in the early 1990s. Although the telescope's low Earth orbit made servicing flights easier, it was also subject to vibrations that reduced its accuracy. Furthermore, it was challenging to examine the outermost reaches of the universe due to Hubble's comparatively tiny 2.4-meter mirror size, which limited its ability to gather light from dim and distant objects. Because of these constraints, NASA, the European Space Agency, and the Canadian Space Agency worked together to develop the James Webb Space Telescope. It was given its name in honor of James Webb, who oversaw NASA's Apollo program from 1961 to 1968. On December 25, 2021, this upgraded space telescope was eventually launched. James Webb was positioned near the second Lagrange point, or L2, which is about 1.5 million kilometers from Earth. In contrast to Hubble, which orbits the planet, because of its advantageous location, James Webb is able to keep a steady orbit away from the Sun, Earth, and Moon, which lessens interference from their heat and light. James Webb can view the cosmos at L2 without being distorted by Earth's atmosphere or affected by light pollution, which is a problem for ground-based telescopes. Furthermore, James Webb's extremely sensitive infrared instruments depend on the colder atmosphere at L2 to operate properly, since they need extremely high cooling. The ability of James Webb to observe in the infrared spectrum is its most remarkable feature. As a result, objects and events that are invisible in the visible spectrum can be seen by the telescope. As it looks farther into space and time that are farther away, it allows us to glimpse them, as they were billions of years ago, when the cosmos was much younger. Nevertheless, the light from these far-off objects has been stretched to longer wavelengths as a result of the universe's expansion, moving it into the infrared spectrum. Because of this phenomenon, which is called redshift, researching the early cosmos requires examining the infrared part of the spectrum. The faintest and most distant objects from the early eras of cosmic history are among the galaxies whose light James Webb can detect, thanks to its infrared capabilities. Revolutionary, huh? But that's not all. The ability of James Webb to investigate exoplanets and their atmospheres is one of its most intriguing features. Through infrared observations of far-off worlds, James Webb is able to identify the chemical composition of their atmospheres, including chemicals that are essential to life as we know it, like carbon dioxide, methane, and water vapor. James Webb's unparalleled sensitivity will enable it to examine exoplanet atmospheres in hitherto unattainable ways, provide fresh perspectives on the habitability of far-off worlds. Because James Webb can identify biosignatures that may indicate the existence of life outside of our solar system, this capacity marks a major advancement in the hunt for extraterrestrial life. James Webb's enormous 6.5-meter primary mirror, which is made up of 18 hexagonal segments made of ultra-lightweight beryllium and thinly coated in gold to maximize its infrared reflectivity, is the centerpiece of its design. Because of its wide mirror, James Webb is able to gather a lot more light than Hubble, which improves its clarity and detail when observing fainter objects. Additionally, the telescope has a 5-layer sun shield composed of a unique substance called Captain that shields it from the sun's heat and maintains the low temperatures required for its equipment. James Webb is able to maintain temperatures as low as -233 degrees Celsius because each layer of the sun shield reflects heat. Its infrared sensors can function at their best in this situation. The near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the near-infrared imager and slitless spectrograph, NIRIS, are just a few of the remarkable scientific instruments that are housed on the Space Telescope. From taking pictures of the birth of stars and galaxies to determining the makeup of far-off worlds, each instrument has a specific purpose. For instance, astronomers may examine the earliest galaxies with NIRCam, and they can study distant galaxies and exoplanets in detail thanks to MIRI, which expands James Webb's view into the mid-infrared spectrum. While NIRIS guarantees accurate pointing and makes it possible to analyze exoplanet atmospheres, NIRSpec enables the telescope to scan numerous objects at once, offering insights into their chemical composition. When combined, these instruments have allowed us to observe objects and phenomena that were previously inaccessible with previously unheard-of clarity. They have also yielded fresh information about the universe's past and the circumstances that could support life elsewhere. Findings from the James Webb Space Telescope have made Proxima B one of the most interesting exoplanets found so far. It is located at 4.24 light-years from Earth and is a prime candidate for the hunt for extraterrestrial life because it orbits within the habitable zone of Proxima Centauri, the star that is closest to our Sun. The scientific community has been tremendously interested in Proxima B since its discovery in 2016, especially in the area of exoplanet research. Scientists use cutting-edge tools like the James Webb Space Telescope, which launched in December 2021 and is intended to view far-off astronomical objects in infrared wavelengths, to gain a better understanding of the planet's environment. This telescope allowed them to get a closer look at exoplanets like Proxima B. The capacity of James Webb to observe the planet's light spectrum using a method known as light spectroscopy marked the beginning of its contribution to research on Proxima B. In order to determine an exoplanet's composition, temperature, and possible habitability, it is necessary to analyze the light that travels through or bounces off of its atmosphere. The presence of water vapor, methane, carbon dioxide, and other gases that could suggest whether the planet is suitable for life are just a few of the minute features in the atmosphere that the telescope can record. In relation to life, we already know that this planet is located in the star's habitable zone, which is an area where the possibility of liquid water on the planet's surface is possible and essential to life as we know it. With a mass roughly 1.7 times that of Earth, Proxima B is somewhat bigger than our planet, only 7.5 million kilometers separated from its host star, which it orbits every 11.2 Earth days. To put it in perspective, Earth is roughly 93 million miles, or 146 million kilometers, away from the Sun. The standard unit of measurement for distances within the solar system is 1 astronomical unit. By contrast, the distance between Proxima B and its star Proxima Centauri is only roughly 5% of that between Earth and the Sun normally. If the star had been anything like our Sun, this would have virtually destroyed the planet. Proxima B, on the other hand, is a red dwarf star that is considerably colder and fainter than the Sun. This implies that Proxima B receives almost the same amount of energy as Earth while being so close to its star, making it, at least in theory, habitable. However, it's not that easy since one side of the planet is constantly facing the star, and the other is always in the dark. The planet is probably tidally locked, which results in sharp temperature differences between the two hemispheres. The planet and its star's gravitational pull causes this phenomenon, leading to stark temperature differences between the day and night sides. The night side might be extremely cold, rendering much of the planet inhospitable, whereas the day side would probably be quite hot. A stable atmosphere, on the other hand, would help mitigate temperature variations by shifting heat from the day side to the night side, which could give hope for habitability. The area that separates the day and night sides may be known as the terminator zone. Due to this kind of heat circulation, there may be a greater potential for life to flourish here, owing to the possibly more temperate conditions. Despite these considerations, Proxima B may face difficulties due to its exposure to radiation from its active red dwarf host star, Proxima Centauri. Strong star flares from Proxima Centauri are known to have the potential to deprive the planet of its atmosphere or expose its surface to extreme radiation. The planet's capacity to hold onto its atmosphere and support life over geological time frames is called into question by this action. However, Proxima B may be able to protect itself from these harsh circumstances if it had a strong atmosphere and a magnetic field. Proxima B's designation as a rocky planet suggests a terrestrial-like structure, perhaps with mountains, valleys, or even oceans, even though we do not currently have direct evidence of the planet's topography or surface composition. In the event that Proxima B proves to be a gold mine, how might the aliens appear? Rethinking habitability assumptions, the discovery of Proxima B has revolutionized our knowledge of exoplanets, their habitability, and the search for extraterrestrial life. Scientists have re-examined long-held beliefs regarding the possibility of life on planets around red dwarf stars, as a result of observations made by the James Webb Space Telescope and other sensors. For many years, it was generally accepted that life was unlikely to exist on planets circling red dwarf stars. About 70% of the stars in the Milky Way are red dwarfs, which are distinguished by their powerful radiation and stellar outbursts. Compared to stars like our Sun, these stars burn at a lower temperature and last a lot longer. Their outbursts were believed to be a major threat to the habitability of planets in the habitable zone. Even though their longer lifespan would offer a stable environment for life to evolve, Recent discoveries about Proxima B, however, cast doubt on this presumption. Furthermore, scientists now know that planets like it might exist more freely than previously thought in our galaxy. Red dwarfs make up the great majority of stars, and many of them have planets orbiting inside their habitable zones. This raises the prospect that the galaxy contains a vast number of Earth-like worlds, many of which might be far closer than previously believed. The discovery of Proxima B has caused a change in the way we hunt for exoplanets that are habitable. This new knowledge puts red dwarf systems at the forefront of future research, whereas the majority of the previous attention was on sun-like stars. Astronomers may find that habitable planets are significantly more numerous than previously thought if they are able to identify additional red dwarf stars and conduct more thorough studies of their planets. It has significant ramifications for our comprehension of life in the universe, especially if Proxima B is home to life, whether it be microbial or more complex as a result.